We cling to it, the comfort of certainty. Science, we believe, holds the answers. It pierces through the veil of ignorance, revealing the objective truth. But what if this truth is more elusive than we think? What if science, like any human endeavor, is not immune to the subtle pushes and pulls of self-interest? Game theory helps us understand decision-making, not just in economics, but in any system where individuals interact, including the world of science. Game theory suggests that truth, or at least the version of truth we accept, can be influenced by the strategic choices of those involved. Think of scientists as players in a grand game. Their goal? To publish groundbreaking research, gain recognition, secure funding. Are we then doomed to navigate a world of subjective truths? Let's dive deeper into the game of science to find out. Imagine a scientific study. Researchers test a hypothesis, their results? Significant. A potential breakthrough. But here's the catch. These results could be influenced by the researcher's own biases, even if unintentional. They might be more likely to see what they hope to see. This is a classic example of confirmation bias. Scientists, like all humans, are prone to such biases. They might interpret data in a way that confirms their existing beliefs, or they might unconsciously design experiments that favor a desired outcome. And then there's the issue of reputation. Scientists with established reputations might find it easier to publish, even if their work is later challenged. Collaboration acts as a system of checks and balances, mitigating individual biases and strengthening the reliability of scientific knowledge. One of the most famous concepts in game theory is the prisoner's dilemma. Two suspects arrested for a crime are interrogated separately. They can choose to cooperate and stay silent, or betray each other by confessing. The dilemma: the best outcome for each individual is to betray the other, but if they both do that, they both end up with a worse outcome than if they had cooperated. This seemingly simple scenario has profound implications for understanding scientific behavior. Imagine two research groups working on a similar problem. They could choose to cooperate, share their findings, and potentially accelerate progress. Or they could compete, keeping their research secret in hopes of being the first to publish a breakthrough discovery. The competitive route, while tempting, carries risks. Game theory helps us understand the strategic calculations that underpin these choices and their impact on the direction of scientific progress. Imagine a shared pasture. Each herdsman can graze their cattle, but if too many do so, the pasture will be overgrazed and destroyed. This is the essence of the tragedy of the commons, a scenario where individuals acting in their self-interest deplete a shared resource. This concept translates surprisingly well to the world of science. The commons in this case can be seen as the body of scientific knowledge. Scientists, driven by the need to publish and advance their careers, might be tempted to prioritize their own research over the long-term health of their field. This pursuit of individual gain can lead to a skewed research landscape, where certain areas are overrepresented, while others remain underexplored. Just like overgrazing depletes the pasture, overemphasizing individual gain in science can deplete the commons of knowledge, hindering collective advancement. Climate change, a topic that has sparked heated debates. Scientists overwhelmingly agree on its reality and human causes, yet dissenting voices persist. How can such disagreement exist in the face of overwhelming evidence? Here, game theory provides a nuanced perspective. It suggests that different stakeholders might be playing different games with different rules and objectives. Scientists, driven by data and evidence, operate within the game of scientific inquiry, their goal to understand and explain the natural world. However, other actors, such as politicians or industry groups, might be playing a different game altogether. Their objectives might revolve around economic interests, political ideologies, or maintaining the status quo. This clash of games, each with its own version of truth, creates a complex and often frustrating landscape. It highlights the challenges of communicating scientific consensus when it intersects with political or economic interests. Scientific truth, unlike dogma, isn't static. It evolves. New evidence emerges, challenging existing theories, forcing scientists to refine their understanding. This iterative process, while fundamental to scientific progress, can be messy and disorienting for those outside the field. Game theory helps us appreciate the dynamic nature of scientific consensus. Think of it as a constantly evolving game where players, scientists, update their strategies based on new information and the actions of others. Consensus emerges not from blind agreement, but from a rigorous process of debate, scrutiny, and the gradual accumulation of evidence. The weight given to certain findings, the interpretation of data, even the direction of future research can be shaped by factors beyond pure scientific objectivity. Understanding these dynamics is crucial for navigating the world of scientific claims. It reminds us that scientific consensus, while the best approximation of truth we have, is not a destination but a journey. Science, for all its noble aspirations, doesn't exist in a vacuum. It's subject to the same forces that shape any human endeavor, including the pursuit of rewards and recognition. These incentives, while essential for motivating scientific progress, can sometimes have unintended consequences. Imagine a funding agency prioritizing research in a particular hot field. Scientists aware of these priorities might be more likely to design their research proposals around those areas, even if other equally important questions deserve attention. This funding bias can lead to a concentration of research in certain areas, potentially neglecting others. Similarly, the pressure to publish in high-impact journals can create a bias towards positive findings. This publication bias can skew our understanding of scientific truth. Scientists, despite their training and objectivity, are human. They carry within them the same cognitive biases that affect everyone. These unconscious tendencies in thinking can influence how scientists design experiments, interpret data, and even present their findings. Confirmation bias, for example, can lead researchers to favor evidence that supports their existing beliefs while downplaying or dismissing contradictory data. This bias can be particularly strong when researchers are emotionally invested in their work or when their reputations are at stake. Another pervasive bias is the availability heuristic. This mental shortcut leads people to overestimate the likelihood of events that are easily recalled, often because they are vivid or emotionally charged. These cognitive biases, while often subtle and unintentional, can have a significant impact on the scientific process. So where does this leave us? Is truth in science merely an illusion, a product of competing interests and subjective biases? Not quite. While acknowledging the influence of game theory on scientific practice, we must also recognize the inherent self-correcting mechanisms within science. Science, at its core, is a process of continuous refinement. Hypotheses are tested, challenged, and revised based on evidence. Peer review, while not flawless, acts as a filter, weeding out flawed or biased work. The open exchange of ideas and data allows for scrutiny, replication, and the gradual convergence towards a more accurate understanding of the world. The key takeaway from game theory is not that scientific truth is unattainable, but rather that it is a complex and dynamic entity. It is shaped by a multitude of factors, some objective, some subjective. Recognizing these influences, both constructive and distorting, is essential for navigating the ever-evolving landscape of scientific knowledge. The pursuit of truth in science, then, is not a passive observation but an active engagement.